Hello everyone. Thank you for watching this presentation, Setting Up Your Postgres Environment Like a Pro. This is the agenda of this presentation. I'm going to talk about myself, the purpose of this presentation, how we started with Postgres, why we chose Enterprise DB, the challenges we met by starting to use Postgres, how we defined standards, and the standards are on the right hand side of this slide. I listed some important ones: server type, server usage, multiple or single instance, software, naming. We have a naming convention. File systems. I'm going to talk about server logon on the three types of servers we have, how to set the Postgres environment, how we do scripting and what scripting we do by standard. I'm going to talk a little bit about the monitoring, how we validate backups. I'm going to tell you what standards we defined for application databases. And the last item of the standards is the superuser API, which we created to help our developers. Now, let me tell you about myself. My name is Benny Rutten. I work as a database administrator in Brussels, Belgium. And as you can see, I didn't start in IT from the beginning. I worked in the Air Force for about 20 years before I switched to become a database administrator. Now, the purpose of this presentation. I made this presentation to show you that good standards create uniformity and ease of management. Also, if you have a uniform environment, it makes scripting so much easier. Not scripting as such, but especially your updates. If you update your script, if you have, for instance, a bug which you want to correct, if all your environments are the same, all your scripts can be the same. And in our case, all our scripts are exactly the same. Whether it's a development environment or a production environment, every script is the same on all servers. Also, if you have standards, you may get happy colleagues because Postgres may not be welcomed as enthusiastically as you might expect, because in our case, we started with a different database provider, and my colleagues, being humans, choose all the time, and we all do it. They choose for the easiest way to go, and the easiest way to go is change nothing and keep your existing database system. So by standardizing, you create happy colleagues, basically, or less disgruntled colleagues. And I must say, in my case, my colleagues accepted Postgres generously, and they treat it like the other database we use. So I can't complain. Let's go to my slides again. So the purpose of the presentation I covered. How did we start? Basically, about 6 years ago, we had a very, how should I say, hostile audit by some other database company, and that made us decide to look if there wasn't an alternative, because open source is what we all like, and the drawback of plain open source is that you're on your own. Basically, you can only ask the community for information, but if you want support, that's something entirely different. So what we were looking for is a robust relational database suitable to run our existing applications, with a flexible licensing model that would allow this software to run in a virtual environment. And most importantly, we wanted dependable, robust 24/7 customer support. That's basically it. This should have been the first topic, because that's the most important for us. Now, why did we choose EDB? Now, EDB's licenses are all in. So if you pay for one instance, you can use all their tools. And let me tell you, EDB's tools get better all the time. The Postgres database covers 100% of our needs. You may have other databases that are very rich in features. They can do, let's say, how should I compare that? You can buy a Ferrari to drive from home to work, but do you really need all the features we were thinking? Because we were paying for a Ferrari, but we didn't use the features of the Ferrari. We use the features of a simple Volkswagen, and that's what I'm trying to show you here. EPAS, Enterprise DB's Postgres Advanced Server, covers 100% of our needs and even more, while we save 90% of the costs. And another reason to choose for EDB is their exceptionally robust 24/7 support. And at the moment that we had to make the choice, we really had no proof that that was the case. We could only rely on their salesperson. But after 6 years, I can confirm you that it's really a strong team at EDB support. Now, what challenges did we encounter? We decided when we chose to implement Postgres, we didn't do it instantly, like next, finish. We wanted to sit back and think about how to create a setup that we could be proud of, even after so many years. We also needed a setup that would be able to get our other database administrators on board, meaning that we wanted to create a set of standards that already existed on our other database servers. Also, the developers, we wanted to make this new, we wanted to make Postgres transparent for the developers. We wanted the developers to see no difference between the old database system and Postgres. And also, we wanted to show our management, which had taken a huge risk by switching to a new database system. And like I told you before, it's so much easier to do nothing and keep the existing system. But my management decided to go ahead with Postgres, and therefore we took the time to make sure that we had a very robust and future-proof setup. And that's what this slide is showing. So, in order to obtain that objective, we decided to set up some standards. Now, standards are some kind of, you could see it as a set of rules which make life for everyone easier. Standards define some requirements, they save money, and they reduce risk. So that was the objective for setting standards. The first standard we created is, or the first standard we decided on, is the operating system. Now, since we already had multiple instances running on Linux, basically Red Hat Linux, we decided that that would be a good choice. Linux is in any case a good choice. It's probably the best OS around. Maybe the traditional Unix systems maybe would be second place for me, but Linux is really the best of the best to us. We also needed to decide how to use our servers. Now, what do I mean by that? At first, since the cost of running Postgres is not that extreme, we decided that we wanted for our production environment a master, a standby, and a witness. I mean, witness being the failover manager of Enterprise DB. And since we want our acceptance environment to be exactly the same as production, so we said, okay, production high available, master, standby, witness, acceptance the same. And initially we wanted the dev environment also to be the same, high available setup. But we soon realized that our developers are not really interested in high available setup. They only want data source to store their test data, basically. And that's how we came up with this. So we decided that a dev server could run multiple Postgres instances, and acceptance production would be high available with only one Postgres instance per server. This is what our dev environment looks like, basically. You see multiple, in this case you see 4 servers with each 6 Postgres instances. Our acceptance and production servers look differently. You see here on this slide 3 servers, we call them nodes in this case. Node 1 on the left, node 2 on the right, and node 3 in the middle. On every server we have a failover manager agent running. Those are the green agents, the green rectangles. And the node 3 runs just an agent, and we call it the witness server. Now those 3 agents together monitor the health of the cluster. And if the master dies or becomes unavailable in some way, the failover managers, those 3 agents together, will promote the standby database or the standby instance to master, basically. Now, how does the standby database keep itself in sync with the master? That's very simple. The standby database has a role that can connect to the master with special privileges, and it replicates everything the master does. And you see here this purple line, that's the slave or the standby database reading from the master. Anything below this purple line is basically plan B, meaning what happens if the streaming replication gets interrupted? In that case, the transaction logs, whenever there is a log switch, the transaction logs are not only copied to the archive location, but also to the standby server. This is a continuous process. So whether or not streaming replication is working, this copying will always be tried. Of course, if this fails, if streaming replication fails, chances are high that the copying of the transaction logs will fail too. But that's no big deal. As soon as the network is repaired, as soon as the network connection works again, those transaction logs will be copied to the standby server. The standby server will read the transactions in these transaction logs, get itself up to date, and continue reading through streaming replication, and the cluster is healthy again. So, what about software? This is very easy. We install everything with yum. Nothing is so easy as typing this yum install name of the software, and it's installed. So that's another standard, yum. Also, naming. We wanted some naming standards. Now we have two types of names. We have basically the instance name, which is only used by DBAs. And we have the database names, which are used by the applications. So as far as instance names go, and we call them in this slide, you see it says PGC for Postgres cluster. Those we decide, but the database names we usually leave up to the application owner to create a name that means something for them. Now every application database or application instance basically gets a set of table spaces, because we don't want to store everything on the same place, in the same directory. We want separate file systems that are mounted on a set of separated storage locations. So for instance, backups, we want to separate our backups physically from the data directory. So basically we have always these 11, is it 11? Yes, 11 table file systems on a server. For every Postgres instance on a server, and for acceptance and production it's only one instance, but in dev it's dev runs multiple instances on one server. We have for every Postgres instance pgadmin, pgarchive A. This is where the database will, or the instance will write its WAL files. We keep it with a tool in sync with this location so that we have a second set of archived WAL files. The WAL files are here, so the database will write the WAL files in a circular fashion in pgwal A. We keep that in sync with a tool to file system pgwal B. The archived WALs is the same story. The archive command, which executes a script in our case, will copy the WAL file to archive location A, and with a separate tool, archive location B is kept in sync with A, so we have always two copies of the archived WAL files. We have a separate backup file system, a data file system, export file system, and here the archive shipped to store the archived WALs that are coming from the master. Now, server logon. We find it important if you log on to a server that you get some information. You want to know who you logged on with. may happen that you by accident log on as root, for instance, which is too much privileges for a database user. So we want to know who we are, what database or what instances could run there, are they running, and also some other info like the version of the instance, the port it listens on, and whether or not it's running, and how to connect to it. By that I mean how to set the environment for that instance. Now, setting the environment for an instance is in many companies done in the bash profile. So as soon as you connect to the Linux server with user Postgres, we use user Postgres because we don't want to use Enterprise DB. It's much too long to type. So we connect as user Postgres. We could set, especially since for acceptance and production we only have one instance per server, we could set the environment in the profile. But we don't do that for two reasons. One, all the bash profiles are the same on all servers. That's part of our standard. We want every script, and the bash profile is a script. All scripts need to be the same. Also, we want the DBA to consciously type the environment he connects to. We have a naming convention that says that the last letter of the instance name is a P for production, A for acceptance, and D for development. If you set the environment in the Linux profile, then chances to make mistakes increase considerably. So that's why all our bash profiles are the same. And you have to set the instance consciously. How do we do that? Now let me show first the logon screens. This is a logon screen for a dev environment. You see, since it's dev, we run multiple instances, and instances that are down are marked in red. I stopped this one just for this screenshot. It shows you the instance name, the version of the instance, in this case Advanced Server 11, the port on which it listens, and whether or not it's up. And here, oh, of course, here on top you see the user which you are logged in with. In this case it's Postgres. And here at the bottom you see set the Postgres environment as follows: ./pgenv. Now that's something I copied from our other database system. The other database has something similar, which I basically reverse engineered. And we see the same on a high available server, in this case a master. So again, you see the Postgres user that you log on with, the instance that could run, or whether it's running or not, and the means how to set the environment. I'll show you in a minute how to do that, and the role of this server. Now this is a master. The next slide is a slave. So this says again the same: who are you, what's running or what could be running, how to set the environment, and the role of this server. In this case it's a slave, which is a standby database. It's 4 seconds behind, it's running 4 seconds behind the master. Now those 4 seconds in reality mean that the standby is real time in sync with the master, because the script to check how far the standby is behind the master runs only every 5 seconds. So if it runs every 5 seconds, the standard margin of error is 5 seconds. And so if it runs behind 4 seconds, it means that it's pretty close to the master. Now, I'm going to tell you about how we set the environment for a database. On every server, we have a file, And that's also something we copied from our other database system. And that file is called /etc/pgtab. And this is the contents of an acceptance server. Now, acceptance servers only host one instance, so you see only here this one line. And every piece of information is separated by a colon. So it says instance name, colon, location of the software, colon, location of the data, colon, port. And how do we use this information? This is the only file that is different for every server. etc pgtab. All our other files are the same, from bash profile through backup scripts, export scripts, any script. This is the only difference. All the information that is special to the instance is read in this file. Now, how do we set the instance? Like I said, I reverse engineered the executable that is standard on our other database system, and I called it PGENV, Postgres Environment. So what do? You type .space PGENV, you get this prompt in white, and you type, consciously, you have to type the instance name, and then you get this output here. It says environment set to, it will tell you the instance name, the data directory, the port, the version, and whether or not it's running. Now, if you want to use this PGENV in a script, you don't care about this output, of course, and that's why you can call it with an argument being the instance name, and then there is no output, but the environment will be set to the values for that instance. Okay, scripts. On every server, we have a number of scripts, of course. If you work as a DBA, you always have backup, cleanup, export scripts. In our case, we have a script to, I'll show you. We have a script here. We have the backup scripts, online full, online incremental. The wrap means that it reads the PGE, the /etc pgtab, and thus executes this script for every instance that's running on the server. And in this case, full backup, incremental differential backup, cleanup to clean up logging and tracing. Then I created here PG vacuum, which sets the resources for the vacuum process higher for night operations and lower again for day operations. And this is a script that runs every 5 seconds. Now the smallest increment you can run a script in the cron tab is 1 minute, but I made it to run every 5 seconds. And then we have an export every day in addition to a backup. You can see here we have a full backup every Sunday, and all other days we have incremental differential backups. And we have every day an export which we keep 2 days. And exports come in handy sometimes. Now, you know that an export is not a backup. An export is a snapshot of the time when you took the export. But sometimes they can come in handy. For instance, something stupid, a table gets dropped or something, or a small mistake where you don't want to restore the whole database. Suppose it's a lookup table that never changes. Then it's easier to go to that export dump, especially since exports in Postgres generate as insert statements. Basically, other database systems generate binary export files. In Postgres, you can open and read the dump files because the dump file contains the create table statement and all the insert statements to insert to get the table filled with data again. So if anything small happens and you can solve it with the export dump file, then you don't need to restore the whole database. Restoring the whole database looks nice, but you have to realize that our systems communicate with banks. Now, some transactions trigger transactions in the banks. So what happens if we restore a database only, let's say, from 2 hours ago, and we trigger those actions in the banks again? That's something we basically can't afford. So that's why those exports are really handy sometimes. Now, let's talk about monitoring. Now, what do we monitor? We use a tool called Nagios to monitor the standard things that may affect your database: disk space, CPU, I/O latency, database connectivity, and most importantly, we monitor the database log for some keywords like error and warning. Now, you may wonder, if you run scripts, how are you going to monitor the success or failure status of your scripts? Now, that's very easy, or we solve that very easy. At the end of the script, it will say success or failure. I will show you an example in a few seconds. Now, at the end of your script, you ask the database the name of its current PG log file, and you write the success or failure status of your script directly into the log file. I will show you. These are 2 excerpts from log files created by the backup script. You see here the first one. This is what it looks like. So it prints a line of equal signs at the top of the message, at the end of the message again, and the message here says error, backup name ended in error. It says check the log file. It mentions a log file here too. And the monitoring system, Nagios, will trigger on this error and will send us a mail with this line. So we immediately know when a backup fails, and we know exactly where to look for the error in this log file. If, in this case here, the second excerpt, if the backup is okay, Nagios will not react to that. But it's in the PG log, and it's one way to check whether a backup was successful or not. Then, making backups is one thing, but how do we know that they are useful? We could trust the message at the end of the backup, which says backup successful, but is it really successful? And we didn't want to rely on that, and that's what we did to solve that. After the backup is finished, we copy the backup set to a dedicated server, and that server cannot modify the backup set. Now, the backup set, of course, remains on the database server, and on the restore server there is only a copy, but still we don't want the restore server to touch or to modify that copy. The only thing the restore server does is restore the backup on its server, and after the restore for all instances is done, we get a mail, and it says, on top here, the title is, in this case, OK, which is usually the case. And if we get this mail, we know that our backups can be used to restore because we just restored them. It tells you for each database the status of the restore, and in attachment it shows you all the details for that restore, which are not important if everything went okay. So if everything is okay, the only thing you care about is this okay, basically. Then we have some other standard which we defined. Every application needs an application database. Now we decided to make every application use not only a dedicated application database, but within that application database, an application schema that is owned by an application owner and can be used by an application user. So when they install the application, and let me show you my slide, when they install the application, they get a database with the name of the application, in this case app01. We create a role which is the application owner, which is app01_owner. We create a user with the name _user. Now the owner, we create for the owner an application schema with the same name as the owner. And the owner can do anything in the schema and is only used to install the application, to create the empty objects. All the rest, the day-to-day application, insert, update, delete, selects, are done by application user. Now the application user cannot drop, for instance, a table. He can only do DML. And what you see here in blue is the instance, which contains a standard databases, template 1, template 0, EDB, Postgres, and then of course our application database. Now the application database writes to a dedicated file system. So the application database has its dedicated file system, which I showed you at the beginning of this presentation. And that leads me to the conclusion that we don't really need enforcing. Actually, what I'm trying to show you now is how we convince our developers to use this setup. Let me go back one slide. How we convince our developers to use this setup. Because if they start with this setup, with the application schema and two roles, an owner, a user, within an application database, if they start like that, it's very easy for us to copy that to acceptance and production, because our developers have no access to acceptance and production. So how do we, let's say, convince them to do that? In order to enforce, actually I use the word enticing here on top, in order to guide our developers into the right structure, we created a set of APIs that they can call. And with one call to a function in the database, they create the whole structure for them. And it makes life for them easy and for us too. And it starts all with a Confluence page which we created. This one. And you see only part of it, but it shows the different Postgres clusters that are available to them. It says instance name, the version, which is not important to them, but anyway, the IP address where to connect to it, and the port. So they have a user. It's called super user. It's a role. And the name sounds like it can do a lot, but the role super user is certainly not a super user. It's a simple role that can call some functions which it doesn't own. And those functions allow the users or the developers to create the environment they need. So they go to pgadmin, log into the Postgres instance and they log into the database Postgres on the instance with the name, with the user, as you can see here on top, they log into database Postgres with user super user. This is the Postgres name. This is the instance name. And they can execute this function. Basically, it says select superuser dot create database and application. Now, if you call a function without argument, you get a help function. It tells you what your options are. And it says this is what will happen. It will create a new application database with the same name as the argument, which is the application name. It creates an owner, a user, an empty schema, and that's it. And so if we call it for real, for instance, with the name test app, so the name of the application is test app, and if you execute this, the output is this. It will say successfully created database test app. It will tell you how to connect to that application. And that's all they need to start working. Now, the APIs we created have some additional functions. They can list databases, they can clone databases, which is very important to them to always start with the same data set when they test something. And they can drop databases. So this concludes my presentation. I hope it was not too boring and maybe you learned something. And if you have questions, let me go to that slide. If you have questions, feel free to ask them. And thanks for watching.
Hi, Benny. Thank you so much. That was really informative. So we have got some questions for you. I hope you can hear me.
Yes, I can.
You can, okay. So our first question is, do you use a PG connection pooler in your production environments? And if so, which is your favorite?
Well, connection pooling is not done at the database level. We have application servers that already have a connection pool, and that's what we prefer. We have no need for it at this time.
Okay. All right, thank you. And you have a PG tab with a location of the data in it. How does this relate to your usage of table spaces?
Well, when you create a table space, you tell in the creation statement where to put it, and it's maintained by Postgres. So it basically, if you look in the data directory of Postgres, you see a little directory which looks like table spaces. It misses some vowels, but in there, Postgres maintains the symbolic link to your custom table spaces. So it's really nothing you should care about.
Okay, so are these links in PG data?
In a subdirectory, it's something like TBL SPC. It looks like table space if you look for it.
Okay. Someone here has said it was a good presentation, and I hope you place PG-env file in sbin or user bin location. I hope that makes some sense.
Well, I looked at our Oracle servers for the location of Aura env, and I put it in the exact same location. So it's in, let me look, user local bin.
Okay. And what size is your database, and how many transactions per second do you process?
Well, we have several databases. The idea when we started with Postgres was to introduce basically microservices. So what we try to do is to have one database for each application functionality. So we have a database for instance, for accounts. We have a database for payments and stuff like that. So we separate everything into really smaller databases. So the largest database we have is only a few hundred gigabytes, I think. I could tell you exactly, but that will take a few moments.
Sure. Okay, we'll move on to the next question. So what happens
Sure.
when you fail? What happens when you fail over to DR? To DR server and start processing there. So how long does it take to switch over to a DR site?
Exactly 70 seconds, because that's the time we decided that the system has to wait to see if the master isn't still alive. So the failover manager has a variable where you can define that, and we took the default. So it waits for 60 seconds to see if the master is still alive, and then it tries another 10 seconds, and then it does a failover. And what happens after the failover is pretty straightforward. Failover manager makes sure that the old master, the one that failed, doesn't get active anymore. We don't want split brain. And on the new master, which was the old standby, we immediately make a full backup. And of course, the failover manager takes care of the virtual IP addresses that those get switched to the new master. And we get a warning. And when we get that, it's our job to see that we create a new standby database from the old master. We could automate that too, but suppose something happens and you get failovers one after the other from one to the other side, that wouldn't be something we wanted. So creating a new master is something we want to do consciously and manually, basically. Well, it's not manual, it's a script you launch, but.
Okay, and last question, because we're running out of time. What is the name of the monitoring tool that you mentioned?
For the moment, we still use Nagios.
Okay.
Nagios.
Okay, that's great. Well, that looks like that's all the questions that we have for today. We are over time. So thank you everyone for joining. And Benny, thanks again for a great presentation. And I hope you all have a great day. Thank you.